Hello everyone, it's a pleasure to be here. I'm a data scientist at Resolver, and I'll be talking about clustering and classification. So the overview of my talk is I'll compare the two approaches and then walk you through a couple use cases of what we've done at my company around different approaches with regards to clustering and classification. So the key difference between clustering and classification is really the nature of whether you have labeled data or how easy it is for you to acquire this labeled data, and whether you look at a problem based on that label or on the existence of those labels. So the whole story around why we work needed to use a topic model is Resolver is a complaint resolution company. So we work in the complaint space and we try to resolve issues. So we have a couple million complaints, and we have when you make a complaint through our website, you label our data in all sorts of ways that helps us resolve your issues. So the main idea there is that with the labels that our users also add to our complaints, we can help companies resolve their issues faster, and we can lead to better outcomes for consumers as well. But we found some trouble with that, which I'll go into a bit later. But first, I'll tell you a little bit of the building block to the solution to that. With regards to clustering, I'm going to be talking about topic modeling and keyword extraction. And topic modeling is a form of, let's say, cool. So with regards to topic modeling, we can identify, let's say, what kind of topics appear in these different documents. Let's assume these sentences are each one whole document. So in this case, for example, in the first sentence, it would be 100% in the topic breakfast, let's say. The second sentence would be 100% in the topic pets. And the third sentence would be a mixture of the two topics, let's say 50% in breakfast, 50% in pets. So the way this LDA approach works is it's a generative process that uses this kind of, the thought process behind it is there's this kind of bag of words that's in each topic, and we assume that people come up with sentences by just pulling out random words from within these topics, and we choose how we mix these topics based on some kind of distribution. So the reason this can work quite well is because, for example, if we had a theatrical and some kind of game-related topics, then play could appear in both of those topics. So you could have different topics that appear quite well. The idea is that in this kind of latent variable space, you will have these different useful topics bubble up. So what you do is you try and estimate, like you set what kind of topics there might be within these based on the set of documents, and then you guess how to build these buckets of words fundamentally that you build your topics around from. But one of the issues around this is what if you come up with some pretty weird topics? So what if the latent space looks good and the algorithm has, let's say, a pretty good perplexity scores, but the topics, once you actually look at them, what if they don't really mean anything, and the topics that you identify are quite problematic? So a big problem around topic modeling is really making sure that your topics are consistent and that you're not having weird random things happening to you, really. So to this end, what works really well is using this technique called word intrusion, where you take the top keywords from within a topic cluster, and then you'd add in a random keyword from another cluster. So I'm hoping you will identify what all of these are. And the reason that this approach works quite well is because this is still something it gives you a kind of quantitative idea of your intra-topic coherence and also gives you a pretty good, this is something that you can actually mechanical Turk out. So this kind of task is something where you're not going to have a very expensive kind of annotation here. And then for us, the second stage in making sure that our topics are relevant is primarily this consolidating the topic and kind of annotating them, which is going to be pretty dependent on what kind of problem you're facing and how difficult your problem is. So kind of going into the example of what the issue was for us. So we work a lot in a kind of complaint data space, and what we were fascinated by was the idea to actually benchmark companies to see where you have trouble in your company, where structural issues based on this complaint data. But what we found is that all these issue types, which are kind of LDA approach generated with some annotation work as well, a lot of these were missing initially from our labels, and our original data set had very low quality due to all sorts of issues. So using this kind of LDA approach meant that we had a pretty good coverage, and we could gain a pretty good idea. For example, this is a bank, and we benchmark it with regards to the banking sector, where the way to interpret this plot is that if somewhere it's green, it means the bank's doing better than the industry. If it's blue, it means we don't have enough data to actually say anything about it. If it's red, then they're doing worse. So this was really the end goal that we were trying to do. We were trying to get a better understanding of what is the kind of structure of complaints fundamentally, and how they work for different companies. Another thing that we were very interested in is whether we could identify big kind of trending issues. So here, we have a telephone company who had a billing issue that hit the news at one point, and we could see in the kind of, these are the proportion of billing issues amongst all their issues per different telco companies, and we could see there was kind of some kind of trouble here. These lines are error bars, so they're kind of our confidence and things. So for some companies, we don't have enough data here. But so we saw that there was, we know there's often big issues with complaints. They can hit the news and cause massive trouble for companies. And what we were very interested in is whether we could then kind of connect back this LDA breakdown of your business with regards to, let's say, some kind of retention or where you are within the contract with a telco, let's say. So this is where you just started your contract, you're in the middle of it, you're ending your contract, and this whole mosaic plot is around the whole telco industry. And then this plot is around this telco that just had that billing issue there. And we were very interested in particularly in this last column, because this kind of showed whether retention would be impacted, whether we wanted to tie back how complaints kind of affect retention with regards to the issues that you have. And we were very happy because these blue blobs here, this is the kind of billing issues, and compared to the industry, there was a massive increase at the end of the contract. So this was kind of what we wanted to show initially, and the LDA approach practically became something like, it became a way for us to kind of place in all these new documents, kind of predict what kind of topic they are, and then based on these topic predictions, then we could then benchmark different companies into these different kind of buckets. So in a way, it was this replacement for our wonky labeling system that we had. So we kind of knew what we wanted to get out of it, really, but what was very, very important in the process in identifying these issues was definitely using word intrusions to identify coherent topics. And then at the next round of annotation, we needed to annotate whole complaints with regards to what kind of topic distributions complaints had according to this new set of like topic sets that we had. So then the next thing that we were thinking of is that, okay, now we've got a pretty good idea of these kind of high-level user journeys, but what if you identify that you've got a billing issue and you know that this is kind of a trouble that's waiting for you and you know it's impacting your revenue as well? What if we could perhaps use some smart keyword extraction to actually drill into the root cause of the issue? So we're, again, a complaint company. Complaints usually have structural issues that they highlight. And there we thought it would be very useful to have this kind of keyword graph where people could, for example, I don't know if you can see those two nodes there, but they're financial difficulty and financial hardship. So they're kind of pretty big issues around consumers being quite vulnerable or being in quite a weak position. So it's definitely something there. Let's say if you had a billing issue and you identified that your consumers were really struggling with paying your bills, then you could kind of dive into there and see how those vulnerable consumers, what are the issues that they're facing and what are the kind of structural problems that you're facing. So what you see here in this kind of keyword graph is bigger nodes are nodes that have more edges and they have more relationships. They're the more relevant keywords for us, and they're also colored in a more the lighter the color, the more nodes it has in it, and the bluer the color, the dark bluer, the less nodes it has in it. So we found that this was a very kind of easy way for you to see what are the actual root causes within the issues that work quite well with once you identify what are these kind of higher level categories. So this allows you to dive in a lot more deeply into it. So to extract these keywords, we use this algorithm called TextRank, which is fundamentally a co-occurrence graph of all the words, and then you run PageRank on it. So the main idea there is that you're doing these kind of walks along these graphs where you also have some potential random chance of kind of just jumping to a different node and starting again when you're kind of updating everyone's PageRank score. And then the PageRank scores are based on all the inbound nodes PageRank scores, kind of scaled by your outbound edges, and the number of outbound edges to reduce those scores. So I think the algorithm itself is less interesting, but what was quite interesting here is that this kind of gave us this more modular way of diving a lot more deeper into these kind of higher level insights that we had. So it allowed us to kind of use the targeting that we had previously to dive into things a lot deeper. I think the difficulty with keyword extraction is that from a kind of product perspective, evaluating it was a lot more difficult. So we really struggled with evaluating our keywords. I think the kind of getting some kind of ranking, formulating it as a ranking problem is obviously a kind of good way to evaluate it, but the problem was obviously around getting the data, around how do we evaluate it with regards to these complaints. So what we kind of opted to do is actually use user feedback, which I think is probably one of the best ways to incorporate into any kind of machine learning that you're doing if you have enough users that you hit, that to try and collect as much of your users' feedback and kind of allow that to happen. So in our case, we'd email some set of our users these keywords that we'd extract, and we'd look at how helpful they found it or not. This was what worked the best for us, really. I think it's quite an easy way to go about it, but obviously we work with quite a large amount of agents who handle complaints, so it was a lot more scalable for us. So after this kind of clustering approach, what what I'd like to get back to is the amazing situation when you do have your labels and they're correct and your data's integrity isn't bad. So another kind of track for us was we were working with, we do a lot of flight complaints as well. They're quite a substantial proportion of all the complaints that go through our website. And a big thing was flight complaints that we were interested in is, can we identify what is the case if the weather is bad and a flight is delayed due to bad weather conditions? How good would we be if we identify that? So in this case, we had a lot more kind of structured data. We knew where the flight was coming from, we knew where it was going to, and we also knew we had about 1,000 samples each of flights that were delayed and flights that weren't delayed. And we had a weather API that we used to kind of grab the weather data around the arrival and departure to see whether we could identify where the issues were. So the core thing here was that I think decision trees are like a really good algorithm. It's definitely not something as cutting edge as all the other talks are talking about in machine learning, but the key advantage of using this kind of approach for us was we were very interested in having quite clearly interpretable weather goals. So what we were very interested in is for example, would our data show, or would this API show, that wind or visibility had substantial implications on whether flights get delayed or not, and whether we could kind of identify these issues in a more algorithmic manner. So to kind of interpret this, this is just a regular kind of, this is a bit of a visualization from scikit-learn for decision trees. If the lighter a box is, the more impure it is, kind of, and the less it splits the categories, the more blue it is, the more good it is at detecting the delayed flights, and the more yellow it is, the better it is at detecting the non-delayed flights, fundamentally. What we found was that it didn't work too bad to identify these different the different weather issues, but obviously a big problem was that a lot of times we had kind of weird things come up with regards to, for example, the time zone of the flight being quite an important feature at some point, and we thought a lot of things were looking a little bit weird. We definitely felt we overfit quite a bit to our training data. So I think that's a good transition to using what an important thing with decision trees is that they kind of bound up space around these decision boundaries around these different variables, and you kind of slice and dice things into getting smaller and smaller clusters where you have these different decisions. And it's very easy for you to overfit, but you have the advantage if it's very easily interpretable, this kind of approach. So one of the kind of standard approaches in getting around this issue is using a decision forest, where the main idea is to bag up your data. Let's just assume these are like 5 different slices of your data, and you just build a tree on this guy, 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 and you just average all their outputs. And the reason this kind of approach works really well, and the really big disadvantage it solves of the decision tree, is that the decision tree will have some kind of error, probably. It's not going to be perfect, at least it won't generalize perfectly. But then the problem is, like, how do you kind of quantify the error of your decision tree? And when your decision tree is just alone with these kind of tree structures, kind of quantifying where it is overfitting and where the problems are rising from is pretty difficult. So the idea is that all these separate decision trees that you set up, if their errors aren't correlated, that means that you're going to have kind of let's say if you have random noise around them all, and it has a zero mean, then averaging these is going to reduce the noise, and it's going to mean that you're going to generalize a lot better than using a single tree, which would overfit. Meanwhile, even if you have these approaches, you can still have a good idea about what are the important features by just looking at these individual trees and looking at the feature importances there and seeing what these structural aspects of things are. So you get this kind of approach of, the advantage of this is you can actually measure a lot better, what kind of, your confidence in your decisions. So with regards to kind of seeing how and what we could do around these decision trees, when you have this kind of structured label data, your evaluation becomes a lot more straightforward around that, whatever you're optimizing, that your labels are centered around. So a very kind of standard approach is, well, the most important thing really is to split your data into these different sets that you'll be looking at, so to make sure that you can generalize as well as you can. Another kind of useful thing when you're using this kind of more bagging approach is that you can also use, if all these slices are different slices of the data, you could use to kind of validate bag 1, you could use all of these guys, and so on. So for bag 2, you could use all the data that wasn't used up, and that's called out of bag scores, when you use your other bags to kind of validate things, and that kind of scoring is very close to your validation set. So it can be quite good if you have less data, so you can use it as a good way to track your validation score. So the main thing, I think, with regards to moving from this, so we had this big problem that we thought we had pretty good data. We didn't have good data. We found that the quality of our data was really rubbish, and that meant we couldn't really go down this pretty straightforward supervised learning approach of setting things up and having a look at how things went. So we needed to go in and kind of utilize more of our on-label data and leverage that. But the kind of last approach to things that I wanted to talk about was a form of semi-supervised learning. So what can you do when you do have, let's say, some amount of label data, and you want to you have a small set of label data, let's say, relatively, and you have a large set of unlabeled data. Like in our case, we've got millions of complaints that might not necessarily match the right kind of label types that we want if we want to predict telcos. So the core idea here, and this is quite a bit more complicated model than all the previous ones, which are very, very simple that I was talking about, is using a language model on your unlabeled data to get a kind of language level understanding of complaints, for example, in our case. So we had to justify why we're making a fake complaint generator at work and what were the reasons for kind of doing that. And then in that case, you can have about a 10 to 20 times less label data to actually get pretty good results with identifying your issue type. So we found that using this kind of transfer learning approach meant it was the best approach we could use for once we had a pretty good idea about the issues of complaints. If we wanted to make a good predictor for different type of issue types based on different company requirements, then this allowed us to kind of leverage all our data, but make sure that we'd have a pretty big improvement. So the green plot here is this kind of semi-supervised approach where you build a language model and then you train the top layers of it to do the document classification itself. And the blue plots are what it would just take from scratch. So as you can see, it's a massive, massive improvement. So the way this fundamentally works is that at the bottom layers, you'll have some kind of idea of what the meaning of words are. Then you'll have middle layers, which are which gives you a good understanding of your language model, and then you just use this language encoder, and you set some decision layers on top of that, and then when you're training your model, first you just train up this guy, and then when you get to the point where you want to train your decision classifier, based on an exponentially decaying amount of weights, you'll be training a decision maker, and you'll use that to then make all these decisions around what do you want to classify. So I think all these three approaches, the kind of useful thing about them fundamentally is that they're all very, very easy to use. So they're quite focused around NLP. We mainly work with kind of complaint data. But when you're tackling these kind of NLP problems, I think using LDA for topic modeling can be very powerful, though it is definitely, if you want to, I think evaluation is very, very difficult, and depending on what kind of goals you have or how complex your kind of goals are. And then keyword extraction is probably even more difficult to clearly define, primarily around the business goals, or how to productionize that, or how to make it something that people are actually buying, or clearly making sure that it's something useful for people, at least in our use cases of diving into complaints. And then using random forests is something very easy. Again, in a couple lines of scikit, you can get around to doing that. And actually doing this kind of transfer learning approach is quite easy as well. It's something where you can get, if you train your own LSTM language model for this, you probably have quite enough data for it. It took us a very short amount of time, about 2 weeks, to get a version of this that we were very happy with, to just train this kind of language generation and then work on the transfer learning aspect of things. So I think that the kind of overview I wanted to give is that these are very easy to use tools that are kind of easy to evaluate as well for these problems, and this is kind of how we went about using them.